Today I'd like to talk about scientific uncertainty. We've talked about the scientific revolution, but now we need to discuss how science has changed as it enters the 20th century. And change it did in some of the most fundamental ways. So let's talk about what science was in the 19th century so that we can get a run-up to the 20th. Science had become the authority for truth. Back in the Middle Ages, if someone wanted to know the truth of anything, they would consult a theologian. But after Newton, if you wanted to discover the truth of something, then you would go to a scientist. And that has remained the case throughout the 19th century. Science was viewed as being triumphant in describing nature. It was inevitable that nature would be totally understood. And people believed that it was only just a period of a relatively short time before all of the laws of nature could be formulated in mathematical terms, and science would then understand how everything worked. There was a prestige in the method of science versus any other methods. And therefore, science emerged as the method of truth discovery, much better than, say, theology or philosophy. And finally, technologists who had more or less been independent of science throughout the history of the world now started to use science as a means by which technology growth was accelerated. Not that technologists always understood, but science gave them clues that simplified their technological developments. We can therefore identify the foundations of science that gave us all of that renewed or excited reliance on science. These are the foundations: determinism, cause and effect, reductionism, and objectivity. Let's talk about each one of them independently for a moment. Determinism. Determinism began with Newton. And determinism is really the belief that the world is governed by fixed laws that can be mathematically described and that govern the motion of things and how bodies interact with each other. It is the concept that the world is like a giant watch, and a great watchmaker has made it, and the world just simply operates according to preset fixed laws. And eventually it was believed that all of those laws would be discovered. And therefore, you could predict how things were going to happen in the future, and you could look backwards to try and understand how things were in the past. Newton believed this very strongly, and he spent a lot of his time trying to back calculate to determine things such as the exact birth date of Christ and what was the phenomena that gave rise to the Christmas star. That shows the confidence that people had in mathematical laws. Second, cause and effect. Cause and effect is simply the interpretation that when an experiment is done, if an effect is seen, then there must have been a cause that is proximate. That is, you can point to what that cause was, and therefore you can interpret the relationship between the cause and the effect. In essence, it says experimentation is acceptable. Third, reductionism. That's a belief that came ultimately from the teachings of Descartes. And in this concept, it says that if you have a huge scientific problem, that problem can be solved by cutting it up into smaller and smaller bits until you get to a problem so small that it can be solved. Then, after you solve that problem, you start expanding, and little by little you can build up until you can solve the huge problem that you started with. Therefore, reductionism is simply a statement that no problem is so large that it cannot be solved by some scientific method, even if it means taking it down to small units and then building it back up again. Objectivity. That basis of science is simply stating that no matter who does the experiment, if the data is to be interpreted, the results will be the same. It says that people don't make a difference, that the data exists independent of people, and therefore science or the laws of nature exist independent of people and their interpretation. I'd like to talk about two scientists that are particularly important during this period of time, during the 1800s. The first that I would like to speak about is Louis Pasteur. How important was he? Well, we are told that at the time of the millennial change, that is in the year 2000, the people in France voted on the most important Frenchman of the millennium. They elected Louis Pasteur. Why, that's quite surprising. Consider other influential Frenchmen like Napoleon or Louis XIV. But no, Louis Pasteur was that man who the French said caused the most fundamental change in the world. Well, what was it that he did? Louis Pasteur began as a chemist and he studied crystals, an important but somewhat isolated discipline. He proved himself to be very adept at relating what he studied to the real world, and that gained him some measure of notoriety. He was found as a man who could be relied upon to link science with an improvement in life. One day, he was approached by representatives from the beer industry of France. They were having trouble because the beer was souring much more often than they could possibly economically stand. So they asked Pasteur if he would help them. Pasteur did extensive investigations, and he eventually found that the beer could be improved and that spoilage would be drastically reduced if the beer was heated to a certain temperature and then bottled. That process, of course, became known as pasteurization. Then, based upon that, he received requests from the milk industry and the wine industry, where there were equivalent problems. And just as he solved the problems with beer, he was also able to solve the problems with milk and wine. The same way, you heat it to a certain temperature, and then it is much longer lasting in its shelf life. In essence, what Pasteur had done was realize that by heating things he could kill the bacteria. And he started to get some kind of inkling that that's what he was doing when he was approached by the silk industry to help them. The silk industry's problem was that the cocoons were beset by some disease no one could identify, and it was killing the caterpillars before they could emerge from the cocoons. Well, what happened is, again, by judicious heating, Pasteur was able to solve the problem and correct the difficulty. Then came a very difficult problem. The chicken industry in France had been suffering because of a high incidence of chicken cholera. It's a disease that is unique for chickens. It's related to cholera among humans, but not exactly the same strain of the disease. But chicken cholera was killing the chickens, and the industry, the chicken industry in France, was really hurting. Pasteur, by this time very, very well known and possessing his own large laboratory, actually Pasteur Institute, was able to conduct some experiments. And in these experiments, he would take a sick chicken, one that had the cholera, withdraw some blood from that chicken, and then he would inject that blood in other healthy chickens. After about 2 weeks, the healthy chickens would develop chicken cholera, and then Pasteur would go through a process of experimentation in which he tried to heal the chickens. One day, after having drawn some serum, if you like, from one of the sick chickens, He was about to do the experiment in injecting and decided, however, that other things got in the way, and that particular syringe full of serum was not used. It was rather just simply left on the counter. Well, it was the time of vacations during July. And when the people in the Institute came back, they picked up the serum in that syringe and remembered that it was out of a sick chicken, and so they knew what to do with it, and they used it to inject new chickens, those that were healthy. After 2 weeks, they found that the chickens who had been injected with this syringe that had sat out on the bench during the vacation were not as sick as others. And therefore they thought, oh, well, there's been some problem. We'll just re-inject these chickens with new serum. So they got new serum out of a sick chicken, and they injected those chickens who had now been twice injected, but they also injected a few more from the same serum batch. In 2 weeks, something very, very unusual was observed. The chickens who had been doubly injected were not sick, but the chickens who had only been singly injected with the new serum were sick in the same way that other chickens had been all the way along. Many scientists would simply ignore the strange findings. Others would discard them and say that a mistake had been made. But Pasteur was creative in his analysis. Something resonated with him. The effect of heat had caused a change. He had already done experiments with heat before, and he was prepared for some knowledge that came out of nowhere for him, out of his memory perhaps, out of the past. And so Pasteur investigated those new chickens much more thoroughly, and he realized that having been partially sick, they had developed some ability to withstand the full sickness, and therefore he invented the concept of vaccination. This is true creativity, understanding what no one else can see, not discarding data, but investigating deviant data, because there's something that has caused that data to be different, and that may be the secret to all. When challenged and said that it was all chance, Pasteur, I think, very, very rightly responded, fortune favors the prepared mind. And Pasteur's mind was certainly prepared to accept the effect of heat on bacteria. Pasteur is the one who gave us the concepts that established the linkage between bacteria and disease and various chemical changes, such as fermentation. Pasteur gave us pasteurization, obviously named after him. He gave us a revitalization of the beer, poultry, milk, and silk industries. And he developed vaccinations not only for cholera, but later for anthrax and rabies. He contributed to the welfare of mankind throughout history from his time forward. The other scientist I'd like to talk about was Charles Darwin. He lived at the same time as Pasteur, although they viewed the world very differently. Darwin was influenced by previous scientists and readily admitted their contribution to his work. His work began as a college student where he went to school and then, upon graduation, did not have a ready job, and therefore he took a position as the scientist aboard HMS Beagle on a trip around the world. During that trip, he noted some very interesting geological formations and some strange things. Up in the mountains of the Andes, he discovered seashells, and he wondered whether the seas had at one time been very high or whether the Andes Mountains had been thrust up from a seabed. And then Darwin went to the Galapagos Islands. They're an archipelago off the coast of Ecuador. And there he saw many species that not only were related but different. And they differed from island to island depending upon the food supply and other factors on each island. He particularly focused on finches, now called Darwin's finches. These finches were a jumbled mess because they had some similarities but some characteristics that were very different, and it was hard to sort them out. Darwin noted characteristics and noted changes in finches from island to island in the Galapagos, and then he went back to John Gould, a zoologist in England who was very famous, and presented the data to him, and Gould threw up his hands almost in despair and said, well, these finches are obviously different species. There's one species of finch for each island. Darwin was unhappy with that explanation. He thought it too easy. Therefore, Darwin did some investigations, and he made the following observations. He realized that the shape of the finch's beak was largely determined by the type of food that the finch ate. If they ate seeds, the beak was strong and robust. If they ate grubs, the beak was long and pointed so that the grubs could be picked out of the trees. If they ate insects, it would be sharp, and if the finch ate buds and fruit, it would be large and rounded. If they ate leaves, it would be smaller because the need for strength in eating them would be diminished. And he noted that all of the finches used their beaks for tools. Therefore, using lateral thinking, Darwin was able to associate the finches with their food, a linkage not made heretofore. Let's view a video that shows some of the concepts that Darwin came up with as he very creatively examined the nature of change in animal life.
I understand your carriage was stoned on the way here tonight.
Well, we're meeting the threat on the streets head on. We're drilling with the Honourable Artillery Company.
Gentlemen volunteers.
In the event of riots, we will back the police.
Every man, as long as he obeys the law of the land, should be free to pursue his own interest in his own way.
Yes, of course.
Charge what he likes for bread or anything else for that matter. Laissez-faire. Let individuals compete and struggle for their advantages. Good night.
Good night. Right.
Whenever I can't sleep, I reach for Malthus. Or as I prefer to think of him, the Reverend T.R. Morpheus. Still warm. 2 brandies.
Yes, sir.
The natural tendency of mankind is to reproduce. Humans can double their numbers every 25 years.
But they don't. A struggle for resources slows growth, and death and disease, war and famine check the population. I know the argument.
Yes, but don't you see exactly the same struggle takes place throughout nature? I don't know why I didn't make the connection before. Why are we not overrun with insects and frogs? Or given the rate at which they reproduce, the number of eggs produced by each and every female?
Nature's broom sweeps away the ugly ducklings, the runts.
Yes, but it's not that simple. It's not that simple. Sometimes it's the ugly ducklings that are better adapted to the situations of life. They have longer legs and can run faster. They have bigger beaks that can crack harder nuts and seeds in harsh winters. They survive, have more offspring. Nature selects them to pass on their traits to future generations.
And where do we fit in?
Well, The sun does not revolve around the earth. Nature does not revolve around man. Man must fall into nature's cauldron. He's no deity, no exception. Once you accept that species can pass into one another, the whole fabric totters and falls.
They'll burn you at the stake for this.
Yes.
But now you have a theory.
Yes, Darwin gave us two books that were earth-shaking. One of them was called Origin of Species, and the other was called Descent of Man. In those books, he said that animals had evolved through a process called natural selection from one condition, one type of body into another one, and that change had occurred because there was a change in the structure, in the genetic structure of the animal that was more favorable. And therefore, this concept of natural selection was eventually reduced, not by Darwin, but by others, to a concept of survival of the fittest. There were challenges. People poked fun of Darwin. They said that he was really a cousin to the monkeys because he advocated that humans and apes had common ancestor. There are some legitimate questions that people could ask about evolution, or the theory of evolution as proposed by Darwin. Some have proposed that the dating of evolution, which of course takes a long, long time, that carbon dating is inaccurate. The reason is that carbon dating assumes that radioactive decay is linear, and that it has been linear for the history of the existence of radioactivity. However, there are very few things in nature that are linear, and it's just as likely that radioactivity could be asymptotic, that it only appears linear because we are at the end of the sequence, but that it could have gone up very, very quickly if you go back further in time. And therefore, the times that are predicted by linearity could be much different if you assume an asymptotic curve. Times wouldn't be as long. So that's one problem. Another problem is what is called micro versus macro evolution. Almost all scientists today agree that microevolution is real, that is, changes within a species. Remember something else, that species is merely an arbitrary definition. It's a little hard to specifically define what is one species and what is another. Remember the problem that Darwin encountered when he took that to an expert in England, took the Finch problem to an expert in England. But macroevolution is dramatic changes from one species to another, and I'll use those terms for simplicity. Most agree that microevolution does occur. Macroevolution, however, is a different matter, and many people dispute that macroevolution has occurred. This is the argument of the missing link. People are trying to say, well, we see changes within people, but we don't see changes from people to apes. Another question about origin of species and the theory of evolution has to do with irreducible complexity. There are some who look at complexity and say there are 2 or 3 steps that had to simultaneously occur for a change to occur that we have observed. And it is impossible, according to Darwin's theory, for multiple simultaneous changes to occur. And therefore, irreducible complexity is a challenge for the theory of evolution. Nevertheless, most scientists believe that evolution is, in fact, the pattern of the world. Why do religionists continue to fight evolution so strongly then? It is simply because some people believe that evolution requires that God not be involved. But there are many evolutionists who also agree that God could have been involved at certain stages of the evolutionary pattern. and therefore, for some, evolution and religion are enemies, but for others, they can exist. The need for God to exist versus only the possibility of existence for some is a threat, but for others, it's a matter of faith, and therefore is no big deal, no big problem. Science is seen in some of the arguments of people as encroaching in the realm of metaphysics and ethics, which have traditionally been areas of religious thought. And therefore, because of evolution, some scientists believe that they can talk about everything and understand everything, including ethics, whereas religionists say that that is really not the basis of science at all. Because of these changes, there are people who believe that the basic values of civilization have been changed by Darwin. That may be the case, and I leave it to you to decide if those changes are real, and if real, are they true? One of the concepts that might explain that and help you in your thinking is this. The stakes in the battle are the continuing existence of a society like the one we have. Do we believe that we can exist and continue to exist according to the rules of civilization over the last 6,000 years, or is there something new that is coming that we need to examine? Darwin himself recognized some of the problems that he personally encountered with his own theory. He said this, "Poetry of many kinds gave me great pleasure, and even as a schoolboy, I took intense delight in Shakespeare, especially in the historical plays. I have also said that formerly pictures gave me considerable, and music, very great delight. But now for many years I cannot endure to read a line of poetry. I have tried lately to read Shakespeare and found it so intolerably dull that it nauseated me. I have also lost almost any taste for pictures or music. My mind seems to have become a kind of machine for grinding general laws out of large collections of fact. But why this should have caused the atrophy of that part of the brain alone on which the higher tastes depend, I cannot conceive. The loss of these tastes is a loss of happiness and may possibly be injurious to the intellect and more probably to the moral character by enfeebling the emotional part of our nature. Hence, Darwin says that in his own life he has lost the desire for art and sees that as a loss of happiness. That may be so, and if we push too hard for a scientific, technological world, we must be careful that we don't lose art along with it. Is it a danger inherent in science? Possibly so. We must guard against it. Frankly, that's one of the reasons for the existence of this course. I want to integrate scientific thinking with the humanities so that we see them both as coexistent and cooperative, rather than as two ends of a spectrum that have trouble talking to each other. Now let's return to our study of science. Darwin's theory did something to science that perhaps was unexpected. He said that these changes in species, what we now call mutations, happened only by chance. He said that there is no law that determines exactly when such a change will occur. Darwin questioned determinism. He brought chance into the scientific picture. Therefore, he questioned Newton's fundamentals. Newton said that time is continuous and constant, that space is continuous and constant, that mass is continuous and constant, and that the world can be described by Euclidean principles. Let's take a look at each one of those. After Darwin, we have some problems. First, what is Euclidean geometry? Euclidean geometry is based on these a priori or before anything assumptions. First, the shortest distance between 2 points is a straight line. Second, 2 parallel lines never cross. Third, 2 non-parallel lines cross at one and only one spot. Newton then derived that mass is a constant that relates time, length, and speed or acceleration. In essence, he established the laws of motion based upon Euclidean geometry principles. But in the 1900s, Riemann, a German mathematician, developed a different geometry based on a different set of assumptions, and his assumptions were these. 1, the shortest distance between 2 points is a curve. 2, 2 parallel lines cross at infinity. Einstein then derived that mass is a variable that depends upon time, length, and speed or acceleration. Let me say that again. Newton said that mass is a constant. Einstein said that mass is a variable. They cannot both be right. Einstein then developed a concept called relativity. Let's talk about it. In relativity, a clock attached to a system that is in relative motion will be observed to run more slowly than one that is stationary with respect to us. In other words, a moving clock runs slower than a stationary clock. Rods appear to contract in the direction of their motion when they are observed to move from rest into uniform motion. In essence, rods get shorter as they move. And the mass of a moving body increases with the body's velocity relative to the observer. In other words, mass gets bigger. So if we look at Newton's formulation for mass, he said that force is equal to mass times acceleration, and mass is a constant. Mass is, in essence, unchanging for a body. Einstein said that energy equals mass times the square of the velocity of light. In essence, mass and energy are both variables, and that the constant is the velocity of light. Now, some people say that Newton was the specific case of Einstein. They say Einstein was right and that Newton was just a specific case. That's not quite true. The reason is that Newton could not be a specific case and say that mass was a constant, because even in Einstein's view, mass would always be a variable. It is only that Newton's law appears to be true. Newton's law is false if Einstein is true. Newton could appear to be true because the changes are so small that we don't note them. But nevertheless, if science is looking for truth, Newton was not it, if Einstein is true. The concept of chance came to us in the 20th century with another dramatic influence, and that is called the uncertainty principle. The uncertainty principle states that you cannot simultaneously determine the position and momentum or mass of a particle. If the particle moves, you cannot say exactly where it is or what its mass is at the same time. Electrons are therefore indeterminate in their momentum and position. That means that electrons can be thought of as a wave as easily as they can of a particle. In fact, there are some experiments that show electrons to have a wave character, and some experiments that show electrons to have a particle character. And we really don't understand what they are if we try and describe them in terms of traditional waves and particles. We also find that positions and masses and other characteristics of particles are expressed by probability and not by exact laws. Therefore, determinism is questioned by these principles of uncertainty. It's very confusing for people. And in fact, William Bragg, a Nobel Prize winning physicist, had a funny comment about it. He said, God runs electromagnetics by wave theory on Monday, Wednesday, and Friday. The devil runs them by quantum theory on Tuesday, Thursday, and Saturday. Okay, we've talked about the effect of these things on determinism. Now I'd like to talk about chaos theory and the effect of modern findings on cause and effect. Chaos theory derives from an experiment that was done a few decades ago on the weather. A scientist was doing a prediction of the weather using a very, very large computer, and he input temperatures and pressures and then allowed the computer to run a very sophisticated program to predict what temperatures and pressures would be like in the future. He had run it many times and had various results encouraging him that he might be able to give some accurate predictions. But one time, in the midst of a run, the computer crashed. Not wanting to lose all of the time that he had put in on the computer, he decided that he would start up the computer again from that point by just simply re-entering the data that he got from his last output. He then re-entered the data and ran the program. To his great surprise, he found that the program gave very, very different results than ever had been obtained before. He was clever, and he decided not to throw that program out, but to investigate why he saw such a deviation. He went back and looked at what had happened and realized that when he re-entered the data, he re-entered the data in 8 decimal points. That is, a temperature might be read as 32 degrees, 0.5, 6, 7, 8, 9, 10, 11, 12. Something like that. 8 decimal points. But then he realized that the computer itself was keeping the decimal points in 12 positions. He investigated and found that the problem arose from the time when he re-entered the data. He re-entered the data as it appeared to him in the output, 8 decimal points. But he realized that the computer kept the data in 12 decimal points. Now you think about it, a temperature that differs only in the 9th, 10th, 11th, and 12th decimal points meant that there would be a significant change in the result. That incredibly small change in temperature or incredibly small change in pressure led the scientists to the following statement. When a butterfly flutters its wings in one part of the world, it can eventually cause a hurricane in another. That's because these pressure and temperature differences that he noted are so small that they would be otherwise insignificant, except that they made a difference. What does that mean about cause and effect? When we see a change, can we really point to the reason for the change? Can we make a linkage between cause and effect? Now let's talk about objectivity. Here's a picture. Is it a duck or is it a rabbit? Well, it can be one or the other depending upon how you see it. In other words, the interpretation of what this picture is depends upon how you as an individual perceive it. Thomas Kuhn, in his book, The Structure of Scientific Revolutions, made a comment about the objectivity and individual nature of perception. What a man sees depends both upon what he looks at and also upon what his previous visual conceptual experience has taught him to see. Translated, that says that each of us has a paradigm, a way of thinking about the world, and we interpret to be consistent with that paradigm. I'm a chemist. I received my PhD in physical chemistry. When I think of the world, and I think of the world of chemistry, I think of it in terms of atoms and molecules. That is my paradigm. But what if atoms and molecules are not real? Then all of the classes that I teach where I use the paradigm of atoms and molecules might be incorrect. The data that I interpret in terms of atoms and molecules might be incorrectly interpreted. So my objectivity, that is the way I perceive the world and the way I interpret data to make it objective, may be in question. Objectivity itself is probably not real. To give you a feeling for that, let me show you a video. The video is self-explanatory. Please look closely.
I'll show you a 1-minute video clip in which I'm going to have you do a count. With an audience this size, it's a very interesting phenomenon. Here's what it looks like. Okay, so there's 6 students, 3 white shirts, 3 black shirts. There's 2 basketballs, they're passing them back and forth. Your task is to count the number of passes in 1 minute between the white-shirted students. Number of passes, they're going to be moving around, so it's complex. I wanted to show it to you. Number of passes by the white-shirted students in 1 minute. Those of you that have seen this, don't blurt out the answer, but it's a very interesting effect where it turns out there's a gender differences on attention to this kind of detail with a lot of action going on. I won't tell you which gender is more accurate than the other, but we'll see at the end. Okay, so here we go. Okay, how many did you get? 18, 17, 13. Okay, that's quite a spread. All right, good. Anybody see anything unusual? Show of hands, anything really unusual in this tape? About half of you. So let me show it to you again. This time, don't count the passes. You're just watching globally what this looks like. How could you not see a guy in an ape suit? Come on. How many of you saw the gorilla the first time? Honestly now. Okay. Actually, that's about right. This is Dan Simon's research at Indiana. It's called perceptual blindness or attention blindness, where you're attending to one task, you miss really obvious things, like a guy in an ape suit. So cognitively, we are primed to look for something. I primed you by giving you a detailed task. I upped the ante by saying one gender was better than the other. By the way, there's no gender difference. And this is a huge problem, in not just dealing with the paranormal and stuff, but all of science. We're primed to look for certain data to fit our theories. We can't help.
Were you surprised by what you saw or didn't see? Isn't it interesting that our minds play tricks on us, that we are not able to perceive some things that are in front of our very eyes because our attention is directed elsewhere? Isn't that the way that paradigms work? That our minds are locked into a particular way of thinking and we may not see the other things. That's why both Pasteur and Darwin were so important to science, because they were able to recognize things that didn't seem right and explore them. So, there have been some changes from 1850 to the present. Here are listed again the 4 fundamental bases of science: determinism, reductionism, cause and effect, and objectivity. I suggest to you that from 1850 to the present, determinism has been eliminated. We now see the world in terms of probability. Reductionism has been eliminated. We now see the world in terms of uncertainty and complexity. Cause and effect has been eliminated. We now see the world in terms of chaos theory. And objectivity has been eliminated. We now see the world in terms of paradigm. So where is science? If it doesn't have its four fundamentals, what is science? We can ask ourselves this question. If science is fundamentally uncertain, why has it been so successful? Why has it caused so much change in the world and accelerated learning and knowledge and technology and the modern life? Well, I think you can have a lot of answers to that, but one of them certainly is science is not entirely wrong. It doesn't give full truth, it doesn't give exact answers, but it gives answers that are good enough that we can proceed with confidence and make the world a better place. Probabilities can be very high. Still, it is not truth, and doubts still exist. So then we ask ourselves a more fundamental, metaphysical question. Can science discover truth? I believe the answer is no. The reason is because science always has the possibility that new data can give new concepts, and therefore you're never sure that it has the truth. On the other hand, it may have discovered truth, but we just don't know. Einstein and Bohr, two famous chemists or physicists of the early 20th century, had a disagreement about the wave-particle duality of electrons and light. They could not resolve their questions, and yet they were both brilliant scientists. One believed that electrons are really dual nature things and all electrons really are something else, but our brains can only perceive what we have had experience with. Ultimately, they were friends but disagreed. Fritjof Capra, a deep thinker of today's generation, says, scientific theories can never provide a complete and definitive description of reality. They will always be approximations to the true nature of things. To put it bluntly, scientists do not deal with truth, they deal with limited and approximate descriptions of reality. That's not quite true either. It is possible that scientists have discovered truth, but they're not sure that they have, and certainly they can't point to anything that is true. They just have to hope that what they've discovered is the truth. So then we ask ourselves, what is the relationship between scientific probability and religious faith? Faith is trusting that you can understand the cause of some effect. In science, you trust that the cause is proximate, that is, nearby in time and space, or is at least explainable. In religion, you trust that the cause is known to God, and that eventually we will come to know the truth. In both cases, there is trust. Both methods require faith. So what are the limits of science? Well, we have certainly found that science is limited in absolute knowledge that what it has discovered is truth. But on the other hand, science is valuable because it gives us power to proceed into the future. It gives us faith, in religious terms, that we can make major improvements and discussions about the world around us. Has science reached its maximum value? I don't think so. I think that science has tremendous opportunities lying before it. The world is more complex than science thought. That just gives greater opportunities for discovery. This era, beginning with the Renaissance and developing from the Enlightenment to socialism, from positivism to scientism, from the Industrial Revolution to information revolution, was characterized by rapid advances in rational cognitive thinking. This in turn gave rise to the proud belief that man, as the pinnacle of everything that exists, was capable of objectively describing explaining and controlling everything that exists, and possessing the one and only truth about the world. This era has created the first global or planetary technical civilization, but it has reached the limit of its potential, the point beyond which the abyss begins. Traditional science, with its usual coolness, can describe the different ways we might destroy ourselves, but it cannot offer truly effective and practical instructions on how to avert them. That somewhat negative view of science was given by Havel, who was the first leader of the Czech Republic. I don't quite agree with it all, but I do believe that science must look beyond just the scientific method. They must look to the humanities. They must find truth in emotion and truth in feeling, as well as truth in logic. Transcendentalism may make a strong comeback in the world before us. There are some great works that I'd like to talk to you about for a moment. Works that are iconic, works that are so perfect for its genre that we think of them as being almost the epitome. Beethoven's Fifth Symphony in music, Plato's Republic in writing, Newton's Principia in science, Shakespeare's Hamlet in drama, Da Vinci's Last Supper in painting. I want you to notice something about those. The symphony is in a language that's universal. Plato's Republic has been easily translated into English. Hamlet is English. Da Vinci's painting is a universal language. But Newton's Principia maintains its name in Latin. That's still a foreign language. And I think that's symbolic. Science today continues to use essentially foreign languages, languages only known to scientists, often mathematical in their orientation, often very much jargon-filled. I think that's a problem. Science needs to get rid of its jargon-filled language and speak in terms that are accessible to everybody. It may be that it's a little more difficult to explain precisely what you want, but it is worth the effort. We need to have a world in which science is not isolated. Science needs to be integrated with all of the other disciplines of mankind. And we shouldn't have an area where scientists feel comfortable and the rest of the world feels strange. That's why, when I was given the privilege of giving the Maser address at the university, my title was Why Scientists Should Read Shakespeare and Why Humanists Should Understand Einstein. I believe that there is too much of a separation between scientists and humanists, that we should work to merge these two disciplines, these two areas, these two concepts. You can learn to talk to each other and perhaps solve the problems of the world. The problems are so complex that surely they need input from all of these people. We should work together. We should not work separately. The tie that binds us all together is creativity. It's critical in these times of uncertainty. It's critical that science, humanities, work together for the betterment of mankind. I hope you will. Thank you very much.